AP Calculus AB, Unit 6, Day 7 lesson. We're going to start with a warm-up. You should pause the video, try these problems, and then unpause it, and we'll check our answers. This is questions from our last lesson and assignment, so it's just a good chance to practice them and see how you're doing. Okay, so assuming you've tried it, I'm just going to add a little review right here of what we're using that we learned yesterday or last time. So f of x gives you the y values of the graph. If you're looking for intervals, there are special intervals. And there are special points. We don't use this one a lot, but it can be above the x-axis or below the x-axis. Also, you can identify zeros. I mean, these are just basic things that are good to know about all these different graphs that we study, just kind of know what's going on. But f prime of x gives you the slope of the function, and the intervals that you find from that, from doing line checks, are increasing and decreasing. And we include the endpoints. Special points could be critical points, stationary points, relative maxes and mins. So a lot of good stuff from first derivative. Second derivative, f double prime of x, gives you the concavity of the graph. From this, you can find intervals where it is concave up or concave down. Special points would be inflection points. So just a quick little rundown of what we talked about yesterday. So we're just looking at pictures for problem one. Identify the x-coordinates of all the critical points. So if the derivative, critical points, if f prime equals 0 or undefined, that's a critical point. So it's peaks and valleys or plateaus. So I would say x equals b, c, e, and f are the x coordinates of those locations. Inflection points: concave down, concave up, concave down, concave up, concave up, concave down. So inflection points are where concavity changes, which generally happens when the second derivative is 0 undefined. But B is an inflection point. It goes from down to up. That cusp could be inflection point. D, E, this one goes up to up, so F is not. G are all the inflection points. 2, identify intervals where F is increasing, so it means the graph is going up. So it'd be A to B, and we include the endpoints. And then C to D to E to F, all one, C to F. Because we include the endpoints, we're not going to break it up C to E, E to F, because we're going to include E for both of them. So just do one big one, C to F. Don't break it up. Concave down would be A to B, parentheses, never include the endpoints for concavity, and D to E. And G to H. So that's where the second derivative is negative, increasing where the first derivative is positive. All right. And then how do we do it without a graph? Number 3 is without a graph. Well, we do line checks. So we got to take the derivative of the function. So g prime of x equals 3x squared minus 12x, and we're going to set it equal to 0 undefined. So g prime x equals, we can factor out of 3x, and then we have x minus 4 equals 0 undefined. And so x equals 0 and 4 are our critical points. So then we do a line check. 0 to 4, test a point. X equals 5, positive, negative, positive. Now I like to draw these little arrows showing the slopes because these are slopes. So increasing, decreasing, increasing, critical point, relative min, right? That's a low point. This is relative max, lots of good stuff. So decreasing specifically is 0 to 4, include the endpoints. Concavity, concave up or down, we got to take the second derivative. Take it out of the first derivative before you factored it. 6x minus 12, unless you really like product rule. Set equals 0 undefined. We get x equals 2. That might be an inflection point. In fact, I know it's an inflection point. The only reason it would be an inflection point is if it was a double root or root with even power on it. So I know this is going to be an inflection point this time, but it's not automatically anytime it's 0 undefined. So we put that on there. We test a point. X equals 3, positive, negative, concave down, concave up. Inflection points. So concave down, it's going to be negative infinity to 2. And we don't include the endpoints for concavity. So that's that. That's mostly what we did yesterday. Today we're going to talk about locating relative extrema, relative maxes and mins. And I did start talking about this on the assignment, and we kind of started talking about, and I've been making notes of it on our line check. So it's something that pretty much doing the work for, but we just got to get a little more technical with it. So we're going to look at the first derivative test for relative extrema. Now, there's a bit of a definition to it, but it's better if you just understand it. Basically, it's kind of a simple idea. If you have a graph, you say, okay, well, this is a relative max right here, right? Which is a peak, non-technical term, or a valley, non-technical term. Technical term would be relative min. How do you identify it? I mean, looking at the picture, it's going up and then it's going down. A peak has to happen after it goes up and before it goes down. So positive slopes, negative slopes, positive slopes. It's really as simple as if the graph is going up and then down, that's a peak. If it's going down then up, that's a valley. So this is what the first derivative test tells us. It says if f prime is positive and then it goes to negative, you're going to get a relative maximum. And that's not something to memorize. Just visualize it. If you're going up and then down, that's a peak, right? And then if you're going down and then up, well, that's a relative minimum. Going down, then up, it's relative min, it's a low point. Don't memorize that. That just should make sense to you. We have to use that to justify some of our answers. So let's see. Let's try a couple examples on the back. And this is actually a problem from our last assignment, page 30624. So the way we did this was we said, all right, let's take the first derivative, 1/2 minus cosine x, and set it equal to 0 undefined. And then we solve for it. You got to solve the trig problem. Alpha equals, when does cosine equal 1/2? Well, it starts at 1, root 3 of 2, root 2 of 2, 1/2. 0, pi over 6, pi over 4, pi over 3. Quadrants 1 and 4 is when it's positive. And specifically, we're looking on 0 to 2 pi here. Got to give some restriction, otherwise get infinite answers. Okay, so x equals pi over 3 plus 2 pi k. X equals 5 pi over 3 plus 2 pi k, but we only want the answers between 0 and 2 pi. So pi over 3 and 5 pi over 3. These are your critical points. Does it bounce off the graph? Is it that issue? Because when we do a line check, So remember, the balance issue for sine and cosine is when you have sine or cosine of something equal to plus or minus 1. So do we have the balance? Nope. Not this time. But watch out for it. All right, so we're going to do a line check. Label a line check. Put your values left to right, smallest to biggest. Put your domain restrictions from the directions on it. Test a point. Tell me what you test. I love 0 for trig. Plug it into f prime. This is one of the biggest mistakes people are going to make. They're going to plug it back into the original function. Plug it into f prime. Cosine of 0 is 1. It's going to be negative, positive, negative. So it's decreasing, increasing, decreasing, decreasing, increasing, decreasing. Relative min right here. Look, you can see it. Relative max right there. You can see it. We are using the first derivative test. Now, the actual relative max value, you'd have to plug this back into the original function to get its value, or relative min. But often you only ask for the location. So you might, like the technical answer might be f of x has a relative minimum at x equals pi over 3, right? Now the justification would be by the first derivative test for relative extrema. On the AP test, you're going to have to do this for response. You have to write this out. And then naming it's not enough. You got to explain how it works, since f prime of x is negative on the left. We could just say 0 to pi over 3. And f prime of x is positive on the right. So it's pi over 3 to 5 pi over 3. That would be a really good, thorough answer with justification. And you could say f of x has a relative maximum at x equals 5 pi over 3 by the first derivative test. For relative extrema, that's the name of it, which is part of what you'll need to write if you're asked to justify your answer. But then you also have to explain how it works, since, and really it's a simple idea, since it goes up and then down. That's all you're trying, but you're saying it more technically, since f prime is positive, going up, where from pi over 3 to 5 pi over 3, and f prime of x is negative on the right, going down on the interval 5 pi over 3 to 2 pi. So those are really good, thorough answers with justification. Tonight's homework makes some references to the second derivative test. Don't worry about that. We're going to talk about that tomorrow. So just do first derivative test on today's assignment. So here's another one. Now this is one that we're going to do a lot of these problems, and there's going to be some on your next test. And people just make all kinds of different mistakes on here. Okay? And if you practice it, it should, I'm going to bring up some other things here too. Now, first of all, you're going to take the first derivative, right? Now, these are just exponents. You're going to multiply 4/3 in front. You're going to get 4x to the, you're going to subtract 1. It's going to be 1/3. This is going to be minus 24/3, which is going to become 8. X to the negative 5/3. You subtract from it, even if it's negative. Okay? And then you're going to set it equal to 0 undefined to find the critical points. Now, you could change these back to radicals and positive exponents and stuff, but I think it's actually easier, if you can get the hang of it, to factor it now, just the way it is. Now, this is where some people are going to get confused. When you factor, like you always have factored before, if you had like 3x cubed minus 6x. You're going to take out the biggest number you can, but then you're also going to take out the smallest exponent that they all have in common. And that's the same thing here. Like, sure, we're going to take a 4 out because we can take a 4 out of 4 and 8. But then x to the smallest exponent. What's the smallest exponent? Negative 5/3 is smaller than positive 1/3. So you're going to factor out x to the negative 5/3. That's your GCF. Okay. So we factor out x with smallest exponent. And that's what we always do, okay? But people get kind of weirded out here when there are fractions and there's negatives and stuff like that, but same exact rule. Now, when you factor it out, it's division. And so when you have x to the 1/3 divided by x to the 5/3, rules of exponents say subtract the bottom one from the top. So you actually get x to the 6/3 positive, right? When you divide this out. And then this one's going to be a -2. So this is x squared minus 2, okay? It should, if you factored out the correct GCF and you've done it correctly, you should usually work out with some pretty nice values, okay? Now, where are the roots? Where are the zeros? Where are the critical points? So this one's going to give you 2 plus or minus root 2, and that is not a balance issue, even though it has a squared. There's 2 distinct roots. This right here, x equals 0, is a critical point. Division by 0 could be a corner or a cusp on a graph. So that has to come here. Don't forget that this can cause its own issues, okay? So then you do a line check. I'm going to bring up some other examples, though, with this, because these just, like I said, people have a lot of trouble with them. You might as well start working hard on them now. We can test a value, x equals, I think I'll put 1 in, which is right around here. And so that's going to be negative 1 over 4. It's going to be negative, positive, negative, positive. Little arrows show the slopes. This is the first derivative, so it's decreasing, increasing, decreasing, increasing. Relative min, relative max, relative min. I'm not going to go through and give the whole total like super justified answer. Now, just stick with me. Do not end this video soon because I'm going to there's some surprises and there's a bunch of other tips I want to give you that'll help you on your homework. So the relative maximum, right now we're going to say it's at x equals 0. But there's something wrong with this answer. And the relative minimum, we're going to say, is at x equals negative root 2 and positive root 2. Okay, but there's something wrong with this answer. So one issue is, one of the things that we got to watch out for, and we got to watch out for this all the time, but there's certain problems where this becomes more of an issue, and this is domain. So the domain of this, what is the domain of this function? Okay, I know we watch out for this on certain logs, natural logs, you got to watch out, square roots. This right here, this is a negative exponent. So if you plug x equals 0 in, you get undefined on the original function. So domain really is all about the original function. X cannot equal 0 on the original function. And so the domain is actually negative infinity to 0 and 0 to positive infinity. This is the domain of this problem. So when you tell me there's an answer where the function doesn't even exist, that doesn't make any sense. So there is no relative max because this graph, this original graph, has a vertical asymptote there. So even though the graph is going up on the left and right on the bottom, it's because there's a vertical asymptote and the function doesn't even exist there. There is no peak. There's no relative max. So you got to watch out. Be really careful here, okay? You got to watch out for domain on the original function. If there's any negative exponents, that's going to be an issue, okay? Also, with these rational exponents, if they have an even denominator, then that's like a square root, which has its own domain issues. The other thing that you got to watch out for is the bounce effect off the graph, those special points. Because with rational exponents, you might be like, oh, because it has, like a fourth. It matters if it's in the numerator or the denominator. So if you have x to the 5/4, that's a fourth root. This is not a balance because the numerator is the thing that tells you that there's 5 roots, because this is the same thing as the fourth root of x to the 5th. So there's 5 repeated roots, okay? Or you could think of it as the fourth root of x to the 5th power. So there's 5 repeated roots here, which is not a problem. It's the even repeated roots, right? But if it was just flipped upside down, this is the one you got to worry about. This is the one that you're going to have to do. Okay, so this is the same thing as the 5th root of x to the 4th. Well, there's 4 repeated roots there. And if it's even, that's when you have to keep it the same sign. So you just got to be really careful with these rational exponents. If the top is, if the denominator is even, not a big deal. Okay, other than it could affect your domain on the original problem. Okay, if the numerator is even, well, that's going to be one of these bounce issues. Okay, so you got to be careful. So at this point right here, they are both odd. But just because you see an even number in the exponent doesn't mean it's going to be even repeated. So today's assignment, anyways, these are tough problems. Just try them, with these rational exponents. Because like I said, I guarantee on the next test, that's going to be some problems that people make lots of different mistakes on. They don't do the derivatives right. They forget the domain. They don't factor correctly. They miss the bounce issues. There's lots of different little things to mess you up on these rational exponent problems. So might as well start paying attention to them. That's it. Try the assignment. Most of them are odds, some evens.